All right, today we're talking about specific kinds of counting problems that involve these words not and or. They're a little bit unique, they're handled a little differently, and they involve two different principles that we will be using, formulas really, as we take a look at these types of problems. The first one that we're going to look at is the complements principle of counting. This principle talks about the number of ways a certain event can occur in relation to the ways it doesn't occur. So there's three formulas here that are all the same formula, just shifted. Like if you think about it from an equation perspective, we've just added or subtracted quantities from the left side to the right side and so forth. So these are all the same things. Let me actually kind of reference the last one as my reference point first. This says that the number of ways for an event to happen plus the number of ways that the event doesn't happen is equal to the total number of ways that anything can happen. So if you would imagine being at Easter and you had options of pie, and there was 3 pieces of key lime pie left. Ooh, yeah, that's what we had at my Easter. And there was like 5 pieces of strawberry pie left. Well, the 3 pieces of the key lime pie would be like n of a. The 5 pieces of strawberry pie would be the n of a prime. It's the not key lime pie. And they add up to the total number of slices of pie, 8. Okay, that's all that this is saying. The number of ways something happens, the number of ways it doesn't happen, add up to the total number of options. The other 2 equations actually just talk about subtraction of it, right? So if you want to know what's the number of pieces of key lime pie, well, you can take the total number of pieces of pie minus the strawberry pie. Same thing. Total how many pieces of strawberry pie are there? Well, it's total number of pieces of pie minus the number of pieces of key lime pie. So these are just manipulations of the same formula. So what we're about to see happen on the next set of questions that are going to use these formulas is we're going to see a key phrase show up, and that phrase is at least. Okay? So the phrase at least one means one or more, right? One or more. And so sometimes it's harder to find the one or more than you might expect. So let me show you the next example. We'll talk a little bit about some reminders about cards and how cards work. And then I'll show you what I mean by this at least principle. Okay, so we're looking at cans of cards. Reminder, there's 52 cards in a deck. There's 4 suits. There's clubs, diamonds, spades, and hearts. There's 13 cards of each suit. Half of them are red. That's the diamonds and the hearts. So there's 26 red cards. Half of them are black. Those are the clubs and the spades. We have number cards. They start at 2 and they go through 10, so there's 9 number cards of every suit. We have face cards, Jack, Queen, and King, so there's 3 face cards of every suit. And then we have the ace, and it doesn't count as a number card or as a face card. Okay. I think that's probably enough of a reminder. If there are questions as we are looking at this, feel free to ask them. Okay, so let's take a look at this question which talks about at least one. This says that we want at least one card that's not a club. So, in other words, we want in our hand at least one heart, or at least one diamond, or at least one spade. That's what this is saying, right? The problem with the word at least one is it means we could be looking for having one of them, or it could be satisfied by having 2 of them, or it could be satisfied by having 3 of these cards, or 4 of these cards, or all 5. And if we take that perspective, we have to find 5 different combinations. The combinations of these things happening where there's 1 of these non-club cards, 2 of these non-club cards, 3 of these non-club cards, 4 of these non-club cards, and 5 of these non-club cards, which means I have to do 5 combinations. That is not the easiest way to do this problem. So when we say this phrase, at least one, what we're going to be thinking of is we're going to be thinking of, what do I want to not happen? So if I want at least one non-club in my hand, what is it that I don't want in my hand?
5 clubs.
5 clubs. That's what I don't want, right? So this is the complement of having 5 clubs. Or you could say all clubs. I just don't want all clubs. That's the description here. Does that make sense? So when you look inside of MyMathLab, they're not going to be putting this in parentheses, I don't think, where it says complement of and having you fill something in like this. But that is what you're going to have to do in order to do this problem efficiently. Otherwise, you're going to do 5 combinations. Okay? So what does this mean? Well, if you take a look at these 3 formulas, what I'm wanting is I'm wanting to use one of these 3. They're all the same, doesn't matter. I'm just going to use the one that's on top. Right? The number of items in A is the number of items in U minus the number of items in a complement. But I'm going to call it whatever my cards that I'm looking for are. So what I'm trying to find out is my number of way of having non-clubs. Right? I want something in my hand that's not a club. So I'm going to be writing these out a little bit more like detailed for the first one at least, and then we'll maybe abbreviate for the next one. So this is the number of ways of having anything, right, any hand. And then we minus the number of ways of having our 5 clubs, or all clubs. Right? The number of ways of having some non-clubs is the total number of ways of having anything, minus the number of ways of having a hand of all clubs. Does that make sense? Okay, now they give you this, and we've found it before, which is why it's in here. The number of ways of having any hand, any 5-card hand anyway, is that 2 million number on top, 2,598,960. That's the total number of 5-card hands from a 52-card deck. But over here, I need to find the number of ways of having 5 clubs. Okay, so just like we talked about before when we encountered cards, these are all combinations. They're combinations because the order you receive your cards in makes no difference, right? You just shuffle them and put them in whatever order the game is you're playing anyway, whatever suits you for what you're trying to accomplish in your game. So how many clubs are there? 13. There are 13 clubs, 13 of every suit. And how many am I going to select? 5, because it's a 5-card hand of 5-card poker hand that's described. Now, let me make one caveat to say this here. The problem that I'm doing here with you in class today is a 5-card poker hand, But I will say that when I was grading the quizzes the last time, some of you were doing 5-card hands when the directions told you to do a 6-card hand. So just pay attention to your directions. Don't assume. This is just like the one she did in class, and just like read right over things. Be careful to read the directions carefully. All right, so we're going to find the 13C5. So I'm going to sort of take another step down here. We're going to just find 13C5. We've actually found this before, but let's run through it again. Obviously, if you want to do 13C5 with the Pascal's triangle and you had it down to 13 rows, you could do that. That would be fine. I'm going to just use our combinations formula since mine was not even written out that far. Mine only went down row 8. So we have 13 factorial on top. The denominator first is the subtraction, so 13 minus 5, which is 8 factorial. And then the combinations has also the 5 factorial from this 5 on bottom. Okay? So we're going to write our 13 down, 13, 12, down to an 8, 11, 10, 9, and 8 factorial. There's the 8 on bottom, and then 5, 4, 3, 2, and 1. So for starters, the 8 factorials cancel. All right, what else can we reduce?
5 and 10.
5 and 10, or you could even do 5 and 2, which makes 10, right? You can do 4 and 3, make it 12. Okay. Yep, 13, 11, and 9. You're right. So we have 13 times 11 times 9.
1,287.
1,287. Okay, 1,287. So this 1,287 is 13C5. So I'm just going to go back to the equation that I was working with already, right? So I'm taking the same equation here, and now I have the 2,598,960 minus 1,287. And what does that give me?
2,597,673.
Did you say 673, Trey? Okay. Do I have a confirmation? Somebody else have that one? Okay, and if you don't already have your calculator out, you're going to need it on every problem just about today, so you might want to grab it. This is the number of hands of cards, so I'll write hands. Show almost all of them, right? Almost all of my hands of cards are going to have at least one club. That's what this is telling me. Okay, any questions on that? Okay, so we're going to do another one. Same process. Now it says we want cards of more than one suit. So not just specifically having something that's not a club, but having more than one suit at all. Okay? So what is this the complement of? What do I want to not happen?
Just one, two.
Yeah. I do not want to have only one suit. Does that make sense? Okay, so it's not like, it's similar to the last one. I didn't want it to be all clubs. This time I don't want it to be all clubs, or all diamonds, or all spades, or all hearts. Okay, everybody good with that? Okay, so we're just going to call it back to A on this one. I'll just use A. So the number of items in A is the number of items in the entire universal set. That's my 2 million number. Minus the number of items in the complement that I've just described. Having only one suit is my complement.
Does it matter which one you do?
Of the formulas? Not at all. Because you're just going to end up either adding or subtracting things to the left and the right to make them work. Yeah. Okay. So this one is the 2 million number, 2,598,960. And then let's talk about finding how many cards there are, or how many hands of cards there are that have only one suit. Now, we found out over here that there are 1,287 all club hands, correct? But if there's 1,287 all club hands, there's also 1,287 all spades hands, right? And there's 1,287 all diamonds hands. We already did clubs. So I've got the clubs, I've got the spades, I've got the diamonds, and then what did you say?
Hearts.
Hearts. And then I've got the 1287 hearts. Does that make sense? So it's 1287 of each of the individual suits of cards. So what I really have over here is I have minus 4 times, and it's 13C5, which I'll write in here, but it's the 1287 that we saw before. So this is my 2,598,960 minus 4 times 1287, because I'm removing all the hands that have all of any of the suits, and there's 4 suits. So my final answer should be less than the last one, because I'm removing 1287 4 times. What do you get?
5,148.
I think, oh, you got for that value? Okay, yeah, I'll write that in. Okay, say that again, Jonah.
5,148.
Okay, 5,148.
Final answer is 2,593,812.
So again, almost all of them, right? Almost all of your hands are going to contain more than one suit. Is that okay? All right. Try another one. At least one face card. I want my hand to have at least one face card. What is that the complement of? That is the complement of having no face cards. All right, if I want at least one face card, what I don't want is no face cards. I can have 1, I can have 2, I can have 3, I can have 4, I can have 5. Don't want to calculate all those. I just don't want the option of having none. So I want the number of ways of having at least one face card, which is the number of ways in my universal set, minus the number of ways of having no face cards. You can use whatever letters you want, it doesn't make any difference. Or you can write out descriptive phrases like I did on the first one if that's easier to keep them in check in your mind of what you're calculating. But it's still the 2,598,960 here. Now we got to figure out the face card situation. No face cards, complement of having no face cards. So let's actually talk real quick about how many face cards there are. How many face cards are there in a deck? 12. So there's Jack, Queen, and King of each of my 4 suits, right? So there should be 12 face cards. Everybody good with that? So if I have 12 face cards in a 52 card deck, how many of my cards are not face cards? 40. Does everybody understand where we got 40 from? Good. So this piece at the end where it says I want things that are the no face cards, that means I need to select from the things that are not face cards, and there's 40 of them to choose from. And how many am I going to choose? 5. Why is it 5?
5 card hand.
Yeah, because I'm doing a 5 card hand.
And it's at least, so you have us.
Up to 5, right. So, okay, we have 40C5. So down here, we're going to calculate the 40C5 next. Are you guys good? I'm happy to slow down if you need to ask a question.
No, it's fine.
Okay.
It was just the number 12.
Oh, okay. Gotcha, where the 12 came from. That's okay, no problem. Okay, so are we, yes, Isabella?
Is there a way that we can do it backwards where we find how many, like, in F instead of finding the complement of it?
Yeah, but the problem is that you're going to have to figure out how many cards would have 1 face card and would have 2 face cards and would have 3 face
That's why we
cards.
have to do the 5 different.
And not only would you have to do 5 of them, but all 5 of them would be more complicated. So let me just show you a couple of them so you can see what would happen. There's 12 face cards, and you'd need to choose 1 of them. But of the other 40 cards, you'd need to choose 4. And then you'd have 12 face cards, and you'd need to choose 2 of them. And of the other 40 face cards, you'd need to choose 3. And you'd have to do this for all 5 of the different options that present themselves. So it isn't that you can't do it, it's just that it's a lot more work. Does that make sense? So this is doable, but just not desirable. Let's do 40C5. 40 factorial on top. What will go on bottom? 35 and 5. 35 and 5. So let's write our 40 out to 35. Okay, is that all right? Will that look okay? Okay, so I'm going to cancel out my 35 factorials. And then what?
4 and 40.
Okay, 4 and 40 leave me with a 10 on top. Now what?
Divided by 5.
Sure, you could divide it by 5. How about we divide it by 5 and 2? You guys good with that? Lovely. There's only a 3 left. Which one do you want the 3 to cancel with?
36.
36. Okay, so 3 with the 36 leaves me with a 12. So my pieces that are remaining are 39, 38, 37, and 12.
That's fine.
Grab a calculator, definitely not wanting to do that by hand.
Should be 658,008. I got something to
Okay, the 658's right. Double check. Just go ahead and multiply through again one more time just to make sure. You good, Trey? Great. All right. That's why we want to double check. All right, so then we'll take this equation that we had from before. So I had the 2,598,960. And we're subtracting our 658,008. How many hands will we get?
1940952.
I think 952.
Yes.
Yep. Okay. Almost 2 million, 1,940,952 hands. This is how many hands will contain at least one face card. That's still most of them, right? I mean, it's about 2 million out of the 2.5 million that contain at least one face card. It's far more unlikely to not have any face cards than it is to have at least one face card. Okay, is that good? Okay, let's try one more like this. Yep.
I'm just making sure, if we were to use one of the other formulas, as long as we're still finding the universal and the complement first, it's gonna turn out the same as this?
Yes, and since you're asking that, let me actually use one of the other ones this time so you can see that it'll work. Sound good? Okay. So the next one wants us to have at least one diamond. So what is the complement of at least one diamond? No diamonds. And I hope that at this point, and if not, I'll actually spell it out, that you see that this phrase at least one translates into no when we look at complement. Having at least one is the opposite of having none of the same thing. So they go hand in hand. Okay, so since we've asked the question, I'm going to use a different one. We're going to do n of a plus n of a complement equals our 2 million, or our n of u. Okay, so that's one of the different formulas. So if I set it up like this, totally fine. N of u means the number of ways anything can happen. That's the 2 million number I keep working with. So in this perspective, I've got my 2,598,960 on the right-hand side by itself. And this piece that I'm looking for, n of a, stays n of a. And I put in here the complement part. So we got to talk about the diamonds. Okay, so how many diamonds are there?
13,
13. So how many cards are not diamonds?
39.
39. 52 minus 13, or you could say 13 hearts, 13 clubs, 13 spades, add them up. It's 39 cards. There are 39 cards, and I'm going to choose 5 of them for my 5-card hand that are not diamonds. So we will take us aside over here and do 39C5. Now, 39C5 is going to be really close to 40C5, right? Should be a little smaller, but it should be pretty close, in the same ballparking area. So we've got 39 factorial on top. What's on bottom?
34 and 5.
34 factorial and 5 factorial. So we're going to write our 39 out to 34. And then I have my 5, 4, 3, 2, and 1. So 34 factorial is gone. Now what?
5 and 35.
Okay, 5 and 35 leaves me with
12.
7.
Oh, 7. Sorry.
It's okay. Yeah, so 35 divided by 5 would be 7.
12 out of
I don't know where you got 12. I don't know. What's next?
We could do 4 and 3 and then make 12.
Okay.
And divide 36.
Sure. So 4 times 3 is 12. 36 divided by 12 would be 3. Okay, now what?
2 and 18.
Okay, so 2 and 38,
Yeah, 38.
right?
Yeah. Yeah.
2 and 38.
Sorry, I'm tired.
It's okay. What's 38 divided by 2? 19. Lovely. All right, so now we have 39 times 18 times 37
Should be
times
time for
3.
19.
Oh, sorry, wrote it wrong. Appreciate that. 19. And then we had 3 and 7. Did I get them all now? 39, 19, 37, 37. I think so. Okay, what value do you get when you multiply these? 575, 757. It's 5 and 7s that just repeat on this one. Is that the same ballpark as the 658,000 on the last slide?
Pretty close.
It's close, right? Like 575,000 over here, we're at 658,000. We're in the same ballpark.
If not, it's in the ticket booth.
We're close. we're close. Okay, so this piece is right here, right? So in terms of this picture that I've written down, since I used the other equation, let me actually make it just a tiny bit smaller so we can see. This piece is an N of A, that's what I'm looking for, plus the 575, 757 equals the 2,598,960. And what would I have to do to solve for my N of A? Yeah, I'd have to subtract this 575 to the other side, right? Like solving equation kind of stuff from high school. So we would be doing subtraction of 575, 757, so it'll move it to the other side. And N of A will be
2023203.
thank you. Too many twos and thirties. All right, 2,023,203 hands. Okay, is that good? Okay, in terms of complicated structure, this is the more complicated of the structures of the two things we're looking at today. So the next one's easier. The primary reason the next one's going to be easier is because when we're looking at what we just did right now, we're considering creating 5-card hands. Or it could have been 6-card hands or 3-card hands, but you're choosing multiple things, right? When we get to the next set, we're only going to be choosing 1 card, not a bunch of cards at once, okay? So let me show you what the additive principle of counting is and how it works. And you've actually seen it before, though you might not quite remember. The additive principle of counting talks about what happens when you take 2 sets and you combine them. So if A and B are 2 sets, then the number of items in the union is equal to the number of items in A plus the number of items in B minus the number of items in their intersection. And if they don't intersect, that would mean that the number of items in intersection is 0. Then this last piece right here falls off. That's 0, it's just not present. So that's the only difference in these two formulas. So the second formula doesn't have the piece at the end because it's equal to 0. We saw this in chapter 2. And let me remind you with a Venn diagram. So in chapter 2, we had sets, and sometimes our sets overlapped, like this. So imagine the left one's set A and the right one's set B. If I were to count everything inside of set A, it'd be everything I just highlighted in yellow. And if I were to calculate everything inside of set B, it'd be everything I just highlighted in green. And the problem in counting like that is that I double counted the part that's double shaded, right? I counted it when I counted the yellow shading, and I counted it when I counted the green shading. So when that happens, I have to remove the double counting, and that's why you have the subtraction of the intersection on the first formula. However, it is possible that the two circles, excuse me that my drawing on the outside is not big enough, but we'll make it bigger so it'll work. Where'd the green go? Let's try it again. Okay, so it is possible that the two circles simply don't overlap, which would look like this. And if the two circles didn't overlap, then I would simply count the stuff in the yellow and I'd count the stuff in the green, and there'd be nothing to subtract because nothing got counted twice. Does that make sense? So that's the difference in these two formulas. The first one, they overlap, so we have to discount it or subtract from it the double counting. And then the second one, they don't overlap, which means there's no double counting to have to subtract off. We just add them together and we're done. Okay, so you ready to take a look? So like I said, all we're doing on these is selecting 1 card. So a single card is drawn from the 52 card deck. And in how many ways could it be the following? So the first one says a diamond, or that should say and, not and, or an ace. Okay, so the first thing you need to decide is which of the two formulas applies. In other words, do they overlap? Can you have something that's both of these things at the same time?
No,
Yes.
no.
Okay, Trey's right. Yes, you can. What is it?
But ace.
It's an ace of diamonds. Is there an ace of diamonds? Yes. So if this had said like a 7 and or an ace, you couldn't, right? You can't have both a 7 and an ace. But they're different attributes of the card. One's telling you the suit and one's telling you the value of the card. So you can have both these things happen at the same time, which means we're going to count the number of diamonds. We're going to add it to the number of aces. And then we're going to subtract off the number of things that are both an ace and a diamond. Remember, that's what that union and the intersection mean. And is the intersection. So when you're saying that, that means and. How many cards are diamonds? 13. How many cards are aces? 4. How many cards are both aces and diamonds? 1. 13 plus 4 minus 1 is 16. Every answer we get on this set of questions has to be less than 52 because there's only 52 cards. And I'm only picking one.
I like this.
Much smaller numbers in this set, right?
I like that.
Much smaller. So there's only 16, and maybe I should say 16 cards. We're actually selecting a single card to remind ourselves. 16 cards we can pick from. Okay, the beginning of it every time, though, is I need to decide, do they overlap? Question number 6. A number card or a red card? Do these categories overlap?
Yes.
Yes. So I need the first one where I subtract off the double count. So we have the number of number cards. So I'll write this one out in words. You can do whatever makes sense to you. Plus the number of red cards. And then I'm going to subtract off the number of red and number cards. They're both red and have numbers. Okay, is everybody good so far? Okay, we spoke about this briefly at the beginning. What's our smallest number card? 2. What's our largest? 10. So from 2 to 10, how many number cards are there? More. 9. 2, 3, 4, 5, 6, 7, 8, 9, 10. There's actually 9.
It's deceiving.
It's deceiving. I know you kind of want to go 10 minus 2, but it's actually 10 minus 1 because you don't have the first one. Just 9. So there's 9, but there's 9
In each color.
in each color, in each suit, actually, not just color.
That's right,
Yeah, so like there's 9 hearts, there's 9 in the clubs, there's 9 in the spades, and there's 9 in the diamonds. So there's not just 9, there's
36.
36.
Each
So there
color.
are 36 number cards. So what we did is we did 2 through 10 of each suit. That's how we got 36. 9 in each suit, 9 times 4 is 36. How many red cards are there?
26.
26. There's 13 hearts and 13 diamonds, so there's 26 red cards total. How many cards are both red cards and number cards?
18.
18. So how did we get 18?
9 plus 9.
Yeah. There's 9 hearts that are 2 through 10, and there's 9 diamonds that are 2 through 10. So there's 18 cards that are both number cards and red. So I need 36 plus 26 minus 18.
18 plus 26.
Mm-hmm.
44.
Yep, 44 cards. Very good.
Wait, how'd you get 18?
There are 2 through 10 of both diamonds and hearts, and those are all my red cards. They're the diamonds and the hearts.
Oh, okay.
That's how. Yep. 2 through 10 diamonds, 2 through 10 hearts. So 9 and 9 is 18. That's good? Okay, next one. Black card or diamond? Do they overlap? No. There are no black diamonds unless you're skiing. Black diamonds. Ski the black diamonds. Yeah, so diamonds are red, right? So there are no black diamonds, which means this one is actually just counting the number of black cards plus the number of diamonds. And if you wrote down like minus the number of black diamonds, it'd be okay. You just would get 0 when you did the calculation. So it wouldn't hurt anything. It's just not going to show up as a value. How many black cards are there? 26. How many diamonds are there? 13. So my total is 39 cards. Last one, black card or a club, do they overlap? Yes, these overlap. So we're going to have the number of black cards plus the number of clubs minus the number that are both black and club. How many black cards are there? 26. How many clubs are there?
13.
Good. How many cards are both black and clubs? The same 13. So this one, these two are at the very end because they're both sort of like special cases that show up and look a little bit weird. The last one because clearly there's no overlap. This one because clearly if I've counted all the black cards, I already counted the clubs. Haven't I? They're already in there. So that's why we see the adding the 13 and the subtracting the 13 come out. So we're still left with the same 26 cards that we had when we just counted the blacks.